Before we continue to program the actual part that processes sound, let me give you a short introduction into signal processing and how we convert our data into sound signals. As I've already explained in part 2 of this video series, we extract data from the audio commands pointer, means we decode it row per row and send the data to an auxiliary array. The auxiliary array is a 28-byte large data block that contains data from each column. Each column carries information about volume, frequency, duty cycle, and if you want to enable FM synthesis or not. We take these informations and feed them our generators, which convert these data sets into sound signals. The computed sound signals are being put into a memory block called buffer. The buffer is being queued to the digital analog converter that converts our buffer data into analog sound. Let's discuss the pulse generator at first. On the left you can see a classic square wave. A square wave separates itself from a pulse wave that its duty cycle has the value 0.5 or 50%. When we multiply 0.5 with the number of samples of one period, we get the length of the first half of our periodic signal. For example, when the frequency of our signal has 100 Hz, that means we have to process 441 samples per second. When we multiply those 441 samples with our duty cycle, the first half of our periodic signal is 220.5 or around about 221 samples large. The other half is 1 minus 0.5 times 441 samples large. In this case also 220.5 or 221 samples. So when we have a pulse wave like on the right, the duty cycle is a number different to 0.5, let's say 0.75. That means that a 100 Hz signal has one half of its signal, that is 441 times 0.75 equals 331 samples large, while the other half has 1 minus 0.75 equals 0.25 times 441 samples equals 111 samples large. If you add those 111 and 331 samples together, you're back at 441 if you neglect the former up rounding. Why is that important now? Well, we will use several loops to achieve that goal to build these signals. But there are some issues we're going to face with the buffer frame. Our buffer is 2000 to 9000 byte large, depending on how fast we're going to play our music. Not every signal fits well into that frame. In the picture you can see two signals. The signal with the lower frequency, the green signal, fits perfectly into the buffer frame, while the blue signal with the higher frequency doesn't fit so well into the buffer frame. The blue signal would sound chopped if we start our signal every time from the 0th position. So we need a sample clock that tells us the starting point of the signal, so that we can continue the signal from the position where we finish to fill up the buffer. What else do we have to explain? Well, the wavetable generator, well, it's pretty self-explanatory. The shape you can see here would be that shape that you can see here. Now let's go to the noise generator. The noise generator randomly generates on and off signals whose frequency and volume can be manipulated. First, a random number generator creates a number between 0 and 1. Then we will let a loop write an anti-series of one of both values into the buffer. The larger that series of the same value is, the browner the noise sounds. The shorter, the whiter. This repeats again and again until we reach the end of the buffer frame. So let's go to the FM synthesis for noise. The metallic sound of the FM synthesis is caused by repetition of an entire memory block of noise within the buffer frame. We store the block like a sample. Well, please do not confound that term with the unit sample we also use in this context. And then we repeat it several times within the buffer frame. The more often in shorter intervals, the higher and more metallic the sound. This was a short excursion. I hope it helped to understand what I want to implement next.